Hello students, welcome to my second video on bond parameters. In the last video, I explained about bond length, bond angle, bond enthalpy and bond order. In this video, I will explain two more bond parameters which are resonance structures and polarity of bonds. Let me explain the fifth bond parameter which is resonance structures. You would be familiar with Lewis structures and you would be knowing how to draw them from various molecules and ions by now. Remember, when you drew the Lewis structures of certain molecules like ozone, carbonate ion, nitrite ion, and so on, you would have been able to draw more than one structure for those molecules. Right? Now, why should I talk about the structure of a molecule? Because it's the structure of a molecule that helps you in understanding the properties of the molecule to a large extent. And it has been found that a single Lewis structure cannot explain all the experimentally determined properties of a molecule. Okay, if that is so, then a molecule should have many Lewis structures, each of which can explain most of the properties of the molecule. But in actual sense, none of these structures would explain completely all the properties of the molecule. Then what is the actual structure of a molecule like? The actual structure of a molecule should be an intermediate, or it should be a combination of all its contributing Lewis structures. And we give a special name to the actual structure of the molecule, which is the resonance hybrid. So how do we call the actual structure of a molecule? It is called resonance hybrid. The different Lewis structures which help us to realize the actual structure of a molecule are called resonance structures or canonical structures. So whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei in the sense atoms, bonding and non-bonding pairs of electrons in the sense shared pair of electrons and lone pair of electrons are taken as the canonical structures or resonance structures. What do we mean by this? We mean that we are considering the different Lewis structures which help us realize the actual structure of the molecule, which is the resonance hybrid, which describes the molecule accurately. And this phenomenon is called resonance. For example, if you take an ozone molecule, you can see that it has two Lewis structures, 1 and 2. In 1, the central oxygen atom is bonded to one oxygen atom by a single bond and to the other oxygen atom by a double bond. Since a double bond is shorter than a single bond, the two bond lengths in this molecule are unequal. But when you do an experimental study of an ozone molecule, you would find that the two bond lengths in the actual structure of the ozone molecule are the same. That is 128 picometers. And this is neither the bond length of a single bond nor it's the bond length of a double bond. It is somewhere between the two. Since the first Lewis structure couldn't explain why the bond lengths in the actual structure of ozone were the same, an alternate Lewis structure is drawn. And this too failed to explain the experimental results. See, the bond lengths in this Lewis structure also are unequal. Okay, but experimental results prove that the bond lengths in the actual structure of ozone were the same. Clear? So what do we understand from this? How will the actual structure of ozone look like? The actual structure of ozone should be intermediate, or it should be in between the two Lewis structures of ozone, which is called resonance hybrid. This idea may be represented by drawing all possible Lewis structures of ozone molecule and putting a double-headed arrow in between them. The Lewis structure 1 and 2 are known as the canonical structures or resonance structures. The phenomenon of resonance between these two contributing Lewis structures is represented by the double-headed arrow in between them. And do note that these resonance structures 1 and 2, they have no real existence. Clear? These two structures, they don't exist in reality. Keep this in mind. And the double-headed arrow may seem to mislead us. We may tend to think that the molecule exists in its first canonical form for some fraction of time, and then it exists in its second canonical form for a certain fraction of time. But that is not so. Okay, do note that there is no equilibrium between these two resonance structures. Clear? The molecule never exists for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. Then what exactly is the actual structure of ozone molecule? The actual ozone molecule will have only one structure, which is denoted by the Roman numeral 3 here. Clear? This is the actual structure of ozone molecule, which is intermediate between the resonance structures 1 and 2. It is somewhat like it is superimposed. Clear? These two molecules as though they are superimposed. So that is how the actual molecule looks like. It's a combination of the two possible Lewis structures of ozone molecule. So structure 3 is also called as resonance hybrid, and this is the actual structure of ozone molecule. And see here, the two bond lengths, they are in accordance with the experimental results. Okay, the actual structure of ozone molecule has equal bond lengths, and this is in accordance with the experimental results. Clear? So, suppose you are asked to draw the structure of ozone molecule, you may show the phenomenon of resonance between the Lewis structures of ozone molecule, and you can show how this leads to the actual structure of ozone molecule, which is the resonance hybrid 3. Clear? The resonance hybrid of the resonance structures or the canonical structures is shown by a triple line. So in this way you may represent the structure of ozone molecule. Let us try to understand how carbon dioxide molecule exhibits the phenomenon of resonance. There are three Lewis structures, that is 1, 2 and 3 for a carbon dioxide molecule. In the first Lewis structure, the central carbon atom is bonded to two oxygen atoms by means of double bonds. In the second Lewis structure, the central carbon atom is bonded to the first oxygen atom by a triple bond and to the second oxygen atom by a single bond. In the third Lewis structure, the central carbon atom is bonded to the first oxygen atom by a single bond and to the second oxygen atom by a triple bond. The normal bond length of carbon-oxygen double bond and carbon-oxygen triple bond are 121 picometers and 110 picometers. But experimentally it has been found out that each carbon to oxygen bond length in carbon dioxide molecule is the same, that is 115 picometers, and this lies in between the bond lengths of carbon-oxygen double bond and carbon-oxygen triple bond. So how will the actual resonance hybrid structure of carbon dioxide molecule look like? Let's see. The actual structure of carbon dioxide molecule is a hybrid, or in other words, a superimposed form of the three resonance structures 1, 2 and 3 of the carbon dioxide molecule. In the actual structure of carbon dioxide molecule, the two bonds between carbon and oxygen atoms would show some triple bond character, some double bond character, and some single bond character. So this idea may be represented by drawing all possible Lewis structures, that is resonance structures of carbon dioxide molecule, and drawing double-headed arrows in between them. So this way we may represent the actual structure, that is resonance hybrid structure of carbon dioxide molecule. One more example for resonance is the carbonate ion. There are three Lewis structures, that is 1, 2 and 3 for a carbonate ion. These structures are also called resonance structures or canonical structures. In each resonance structure of carbonate ion, there are two single bonds and one double bond between carbon and oxygen atoms. Since a double bond is shorter than a single bond, the bond lengths in this molecule are unequal. But experimentally it has been found out that the three bond lengths in carbonate ion are the same, which is in between that of carbon-oxygen single bond length and carbon-oxygen double bond length. So this single Lewis structure, based on the presence of two single bonds and one double bond between carbon and oxygen atoms, is inadequate to represent the ion accurately. For this reason, the actual structure of carbonate ion is best described as a resonance hybrid of its three Lewis structures 1, 2 and 3 as shown here. Students, if you simply place each resonance structure of carbonate ion one over the other, you would get the actual resonance hybrid structure of carbonate ion. That is, it is the superimposed form of the three resonance structures of carbonate ion. Clear? The phenomenon of resonance between the three contributing Lewis structures of carbonate ion may be represented by drawing double-headed arrows in between them. The resonance hybrid of these three resonance structures is indicated by the triple line shown here. So, which is the actual structure of carbonate ion? This is the actual structure of carbonate ion. It is also known as resonance hybrid. Clear? Since the actual structure of carbonate ion is a hybrid of the three resonance structures, that is 1, 2 and 3, each of the bond in the resonance structure between carbon and oxygen atoms would show some double bond character and some single bond character. Clear? Now students, do concentrate on what I am going to tell you next. When you draw the resonance structures of carbonate ion, don't forget to show that each oxygen atom that has a single bond has the negative charge and the atom that has the double bond does not bear the negative charge. So, in the second Lewis structure, the oxygen atoms with single bonds possess a negative charge each, while the oxygen atom with a double bond does not bear a negative charge. Similarly, in the third Lewis structure, the oxygen atoms with single bonds possess a negative charge each, and the oxygen atom with a double bond does not bear a negative charge. That is why resonance structure, that is in each resonance structure of carbonate ion, the negative charges are placed on oxygen atoms which are bound to the carbon atom by single bonds. Clear? But in the resonance hybrid, for instance, since all the three CO bonds are identical, it is not possible to specify which oxygen atom has the negative charge. That is why the two negative charges on the carbonate ion are represented as superscript outside the square bracket enclosing the actual structure of carbonate ion. So this is all about the resonance structures of carbonate ion and its resonance hybrid. What are the characteristics of resonance? The canonical structures or resonance structures, they don't have any real existence. I told you they don't exist in reality. Remember? They are only imaginary. Only the resonance hybrid, which is the actual structure, has the real existence. Clear, children? Now, resonance averages the bond characteristics as a whole. As a result of resonance, the bond lengths in a molecule become equal. That was what we learned from the examples of ozone, carbon dioxide molecule and carbonate ion. The resonance hybrid has lower energy and hence greater stability than any of its canonical structures or resonance structures. So, which structure has the lowest energy? The structure of resonance hybrid, which is the actual structure of the molecule, has lower energy. Clear? Greater is the resonance energy, greater is the stability of the molecule. Okay, if the resonance energy is greater, stability of the molecule will be greater. Greater is the number of canonical forms with nearly same energy, greater is the stability of the molecule. Clear? We move on to the sixth bond parameter, which is polarity of bonds. The existence of 100% ionic bond or covalent bond represents an ideal situation, and this can happen only in our imagination but not in reality. In reality, no bond or a compound is either completely ionic or covalent. So, there is no bond that is 100% ionic. So, there is no compound that is 100% ionic. Similarly, there won't be any bond with 100% covalent nature. So, there won't be any compound that is 100% covalent. For example, the two hydrogen atoms in hydrogen molecule are covalently bonded to each other. So, hydrogen is a covalent molecule. That is what we say, right? Although the two hydrogen atoms are bonded by a covalent bond, you cannot call it 100% covalent molecule. Why? Because it has some ionic character in it. Shall we study about this in detail? What do we mean by partial ionic character of covalent bonds? There are two types of covalent bonds. They are non-polar covalent bonds and polar covalent bonds. Firstly, let me explain what non-polar covalent bonds are. When a covalent bond is formed between two similar atoms, do note that these are two similar atoms. Clear? The shared pair of electrons is equally attracted by the two atoms. That is, the shared pair of electrons is situated exactly between the two identical nuclei. Such a bond is called a non-polar covalent bond. Some examples of molecules which have non-polar covalent bonds are hydrogen, chlorine, oxygen, nitrogen or fluorine. Now look at oxygen molecule. In oxygen molecule, the covalent bond is formed between two oxygen atoms. There are two shared pairs of electrons between them and they are equally attracted by the two oxygen atoms. Since the shared pair of electrons in oxygen molecule equally belong to the two oxygen atoms, they are situated exactly in between the two atoms. So the covalent double bond between the two oxygen atoms is a non-polar covalent bond. So oxygen molecule is a non-polar covalent molecule. Similarly, hydrogen, it is a non-polar covalent molecule. Why? Because the two hydrogen atoms in hydrogen molecule are bonded by non-polar covalent bond. Clear? The second type of covalent bonds are polar covalent bonds. When a covalent bond is formed between two different atoms with different electronegativities, the shared pair of electrons is displaced towards the more electronegative atom. Now look at the formation of a covalent bond between hydrogen and chlorine atoms. Are they similar atoms? No. Hydrogen and chlorine are two different atoms, right? The electronegativity of hydrogen atom is comparatively less than that of chlorine atom. So which atom has more electronegativity here? Chlorine atom. Clear? Therefore, in hydrogen chloride molecule, the shared pair of electrons between hydrogen and chlorine atoms would be displaced towards the more electronegative chlorine atom. Therefore, the more electronegative chlorine atom acquires a partial negative charge and the less electronegative hydrogen atom would acquire a partial positive charge. Such a bond is called a polar covalent bond. So to sum it up, the bond between hydrogen and chlorine in hydrogen chloride molecule is polar. Why? Because the shared electron pair is displaced towards the more electronegative chlorine atom. Such molecules having oppositely charged poles are called polar molecules, and you can compare them to the poles of a magnet. Just like a magnet with two poles, polar molecules have a positively charged pole and a negatively charged pole. Some examples of polar covalent molecules are water, hydrogen fluoride, ammonia, and so on. Let's study about dipole moment, which is another important topic under the sixth bond parameter, polarity of bonds. In a polar molecule, one end of the molecule is negative and the other end is positive. So in a polar molecule like hydrogen chloride, there are two poles present, just like that in a magnet. For this reason, a polar molecule is said to possess an electric dipole. Now, when you simply write the chemical formula of your molecule, say hydrogen chloride itself, will you write any charge over the chemical symbols of hydrogen atom or chlorine atom? No. You simply write HCl as the chemical formula of hydrogen chloride, right? That's it. Why? Because a molecule as a whole is electrically neutral. Note this point, students. A molecule as a whole is electrically neutral. Now look at HCl molecule. There's a partial positive charge on hydrogen atom and a partial negative charge on chlorine atom. In this case, the unit positive charge on hydrogen atom is equally balanced by the unit negative charge on chlorine atom. So chlorine molecule as a whole is electrically neutral, and that's why we don't write the charges over the atoms in a molecule when we write its chemical formula. We just write HCl as the chemical formula and not H plus Cl minus as the chemical formula of hydrogen chloride. Clear? Now, is there any means to find out how much a molecule is polar by some parameter? Yes, it's possible. The extent of polarity in a molecule is expressed in terms of a parameter known as dipole moment. Okay, dipole moment is the parameter using which you can find out how much a molecule is polar. And dipole moment is usually designated by the Greek letter mu. And what's the definition for dipole moment? It is defined as the product. Okay, it is the product of the value of the charge. Okay, if it is 1, you write 1. If it is 2, you write 2. Okay, so it is defined as the product of the charge and the distance between the centers of the positive and negative charge. So what is the formula to find out the dipole moment mu of a molecule? It is equal to the product of the charge and the distance of separation between the positive and negative charges. Clear? Dipole moment is expressed in d by units, which is capital D. 1 d by equal to 3.33564 into 10 power minus 30 coulomb meter, where C stands for coulomb and M stands for meter. Dipole moment is a vector quantity because it has both magnitude, it has value and direction. Dipole moment is represented by a crossed arrow with its tail at the positive end and arrowhead at the negative end. Now look at hydrogen fluoride molecule. The electronegativity of hydrogen atom is comparatively less than that of fluorine atom. Okay, due to the high electronegativity of fluorine atom, it attracts the shared pair of electrons between hydrogen and fluorine atoms towards itself. So the electron density in hydrogen fluoride molecule shifts towards the fluorine atom. And this arrow symbolizes the direction of shift of electron density in the molecule. Clear? Dipole moment and molecular structure. Firstly, I will explain about dipole moment in polar diatomic molecules. A polar diatomic molecule has two atoms bonded by a single bond. So how many bonds are there between the two atoms? Only a single bond is there between the two atoms in polar diatomic molecules. Okay, in such a molecule, the dipole moment of the bond gives the dipole moment of the molecule. So what will be the dipole moment of a molecule having only two atoms bonded by a single bond? It will be equal to the dipole moment of the single bond between the two atoms. Look at hydrogen chloride molecule. It has only two atoms bonded by a single bond. The dipole moment of this single bond can also be called as bond dipole. Clear? The dipole moment of a bond is also known as bond dipole. So how will you find out the dipole moment of HCl molecule? It will be equal to the dipole moment of the single bond in HCl molecule. In other words, the dipole moment of HCl molecule is equal to the bond dipole of HCl molecule. Note that greater the difference in the electronegativity between the bonded atoms, greater is the dipole moment. Now look at the order in which the dipole moment decreases in the halides. See, hydrogen fluoride, the dipole moment of hydrogen fluoride is the greatest when compared to the dipole moments of hydrogen chloride or hydrogen bromide or hydrogen iodide. Okay, why? Among these, the difference in electronegativity is greatest between hydrogen and fluorine atoms of HF molecule. That is why the dipole moment of hydrogen fluoride is greater than the dipole moment of hydrogen chloride. Why is the dipole moment of hydrogen iodide the least? Because the difference in the electronegativity between hydrogen and iodine atoms of hydrogen iodide is the least. That is why dipole moment of hydrogen iodide is the least here. Clear? So, greater the difference in the electronegativity between the bonded atoms, greater would be the dipole moment. Now, what about the dipole moment in polar polyatomic molecules? Polyatomic molecule has more than one polar bond. Okay, there are more than one bond in a polyatomic molecule. Clear? So the dipole moment of a polyatomic molecule depends not only on the resultant dipole moment of all the individual bonds, but also on the spatial arrangement of all the bonds in molecules. So the dipole moment of a polyatomic molecule is the sum total of the value of all the individual dipole moments of the bonds plus the arrangement of each bond in space. This is how we find out the dipole moment of a polyatomic molecule. Carbon dioxide and water are both triatomic molecules, but the dipole moment of carbon dioxide is 0, whereas that of water is 1.85 d by units. Why? I'll first explain about the dipole moment of water molecule. It has a bent structure, C, and has two OH bonds oriented at an angle of 104.5 degree. Now, which among these three atoms of water molecule is more electronegative? Oxygen atom is more electronegative than the two hydrogen atoms. Since oxygen is more electronegative than these two hydrogen atoms, it has this tendency to pull the shared pair of electrons towards itself. So what will happen? The shared pair of electrons between oxygen and hydrogen in the first bond would be displaced towards the oxygen atom. Okay, same is the case with the shared pair of electrons between oxygen and hydrogen atoms in the second OH bond. Okay, the shared pair of electrons in this bond will also be displaced towards the more electronegative oxygen atom. So hydrogen atoms get a partial unit positive charge each, and the oxygen atom gets 2 units of partial negative charge. Now, how will you draw the crossed arrow for the first OH bond? Since hydrogen has a partial positive charge, the tail end of the arrow will be placed near the hydrogen atom, and the arrow head will be on the oxygen atom. In the same way, you would draw the crossed arrow for the second OH bond also. I told you that dipole moment has both value and direction. Now look at the direction of the two individual bond dipoles. Both of them are directed towards the more electronegative oxygen atom. So they are pointing in the same direction, and hence they don't cancel each other. Therefore, the dipole moment of water is equal to the sum of the dipole moments of the two OH bonds, in other words, sum of the two bond dipoles. Hence, the net dipole moment of water is equal to 1.85 d by. You can also convert d by into Coulomb meter. How? You can just multiply 1.85 with 3.33564 into 10 power minus 30 Coulomb meter. On solving this, you get a value of 6.17 into 10 power minus 30 Coulomb meter. So this is the dipole moment of water. Having explained about the dipole moment in water molecule, I will now explain about the dipole moment of carbon dioxide molecule. Carbon dioxide has a linear structure and has two CO double bonds oriented at an angle of 180 degrees. Students, what should come to your mind first when you look at a molecule? You can see that there are three atoms, two oxygen atoms and one carbon atom here, right? So first of all, you must find which among these atoms is more electronegative. Clear? The two oxygen atoms are more electronegative than the central carbon atom. So the shared pair of electrons between oxygen and carbon in the first CO double bond would be shifted or displaced towards the more electronegative oxygen atom. Same is the case with the shared pair of electrons between carbon and oxygen atoms in the second CO double bond. Why? Because oxygen is more electronegative when compared to carbon. So oxygen atoms have the tendency to attract the shared pair of electrons towards themselves. Okay, when the first oxygen atom attracts the shared pair of electrons in the double bond towards itself, what will happen? the electron density here will shift towards oxygen atom, first oxygen atom. Similarly, if you take second oxygen atom, it is more electronegative when compared to carbon atom. So this has the tendency to attract the shared pair of electrons in the double bond towards itself. So what will happen to the electron density here? There will be a shift in the electron density towards the more electronegative oxygen atom. Clear? So oxygen atoms get a partial negative charge each, and the carbon atom gets 2 units of partial positive charge. Now how will you draw the crossed arrow for the first CO bond? Since oxygen has a negative charge, the arrowhead, the arrowhead will be placed near oxygen atom, and the tail end of the arrow will be on the carbon atom. In the same way, you would draw the crossed arrow for the second CO double bond. Now, look at the direction of the two individual bond dipoles. Both of them are pointing in opposite directions. Clear? And hence, they cancel the effect of each other. See, the bond dipoles are pointed towards opposite directions. So, the net dipole moment of carbon dioxide will be equal to 0. Clear? That is why carbon dioxide has a dipole moment value of 0, while water molecule has a value of 1.85 d by units for its dipole moment. The dipole moment of beryllium fluoride is 0. Why? Let's analyze. Beryllium fluoride has a linear structure. It has two BeF bonds that are oriented at an angle of 180 degree. Now look at beryllium fluoride molecule. How many atoms are there? There are 3 atoms, 1 beryllium atom and 2 fluorine atoms. Among these, which ones are more electronegative? We know fluorine is the most electronegative of all the elements in the periodic table. So, which atoms are electronegative here? More electronegative here? Fluorine atoms are more electronegative. So what will happen? Fluorine atoms being electronegative, they have the tendency to attract the shared pair of electrons towards themselves. Okay, that is why the shared pair of electrons between beryllium and fluorine atoms in the first BeF bond would be shifted towards the more electronegative fluorine atom. Same is the case with the shared pair of electrons between beryllium and fluorine atoms in the second BeF bond. So, fluorine atoms get a partial negative charge each, and the central beryllium atom would get 2 units of partial positive charge. Now, how will you draw the crossed arrow for the first BeF bond? Since fluorine has a negative charge, the arrowhead will be placed near fluorine atom, and the tail end of the arrow will be on the beryllium atom. In the same way, you would draw the crossed arrow for the second BeF bond. Now look at the direction of the two individual bond dipoles. Both of them are seen pointing towards opposite directions, and hence they cancel the effect of each other. That is why the net dipole moment, or the sum total of all the bond dipoles in beryllium fluoride is 0. Dipole moment of boron trifluoride is 0. Why? Look at the structure of boron trifluoride molecule. It has a trigonal planar structure, and it has 3 BF bonds that are at an angle of 120 degrees to one another. Now look at the dipole moment, the direction of each dipole moment of BF bonds. The dipole moment of each BF bond is oriented towards fluorine atom in opposite directions. Why? Because the fluorine atoms are electronegative when compared to the central boron atom. Now look at the dipole moment that is circled in blue here. This is the resultant. Clear? This is the resultant of the dipole moments of these two BF bonds. Now if you look at the direction of the resultant dipole moment of these two BF bonds, you would find that it is equal and opposite to the direction of the third BF bond. Now, if you take the sum of the dipole moment of the third BF bond and the resultant of the dipole moments of the two BF bonds, you would find that they cancel the effect of each other as they are pointing in opposite directions, and therefore the net dipole moment of boron trifluoride molecule would be 0. In the same way, if you try to add the resultant dipole moment of any two BF bonds in BF3 molecule, say these two BF bonds, these two BF bonds, or these two BF bonds, with the dipole moment of a third BF bond, you would find that they cancel the effect of each other as they tend to point in opposite directions. Students, you may check this out yourself. Try adding the resultant dipole moments of any two BF bonds with the third BF bond. You would surely get 0 as the net dipole moment value for BF3 molecule. So this is everything about the dipole moment of boron trifluoride. Dipole moment of NF3, that is nitrogen trifluoride, is lower than that of NH3, that is ammonia. Why so? Let's investigate. First of all, look at the structures of nitrogen trifluoride and ammonia. Both of them are pyramidal in shape. In both cases, the central nitrogen atom has a lone pair of electrons on them. Clear? The dipole corresponding to the lone pair on nitrogen atom is called orbital dipole, and this is represented by the black crossed arrow which is placed near the lone pair of electrons on the nitrogen atom of both NF3 and NH3 molecules. Clear? Now observe the direction of the orbital dipoles. The orbital dipole, due to the lone pair on the central nitrogen atom, points away from the nitrogen atom in both NF3 and ammonia molecules. Remember, I told you before, greater the electronegativity difference between the bonded atoms, greater would be the dipole moment. Interestingly, although fluorine is more electronegative than nitrogen, the resultant dipole moment of NF3 is lower than that of ammonia. Okay, this is an interesting case. It should have been the opposite, right? The resultant dipole moment of NF3 should have been greater than the resultant dipole moment of ammonia. It's just the reverse here, right? Now, let's investigate why this is so. Now look at the direction of the individual bond dipoles of NF bonds in NF3 molecule. They are seen to point in a direction that is opposite to the direction of the orbital dipole, right? Direction of each bond dipole is from nitrogen to fluorine. This is because fluorine is more electronegative than nitrogen. That is why the electron density is seen to shift from nitrogen to fluorine in the case of the bonds in NF3 molecule. The resultant dipole moment corresponding to the sum of the individual bond dipoles of the three NF bonds is denoted by the blue crossed arrow, and its direction, this is opposite to that of the orbital dipole. Clear? Hence, the orbital dipole, due to the lone pair on nitrogen, partly cancels or decreases the effect of the resultant nitrogen fluorine bond moments, and this leads to the low dipole moment of NF3. In ammonia molecule, the orbital dipole is in the same direction as the resultant dipole moment of the three NH bonds. See, the direction of each bond dipole is from hydrogen to nitrogen here, as nitrogen is more electronegative than the hydrogen atoms. Clear? Hence, the net dipole moment of ammonia molecule is the sum of the orbital dipole due to the lone pair on nitrogen and the resultant dipole moment of the three NH bonds. Clear? That is why dipole moment of NF3 is lower than that of ammonia. Students, remember when I explained about polarity of bonds, I told you that no bond is 100% covalent or 100% ionic in character. Although in an ionic compound, the bond is said to be 100% ionic, in the actual sense, it has some covalent character also in it. So, just as a covalent bond has some ionic character, the ionic bond will also exhibit some covalent character. And it was Fajan who explained the partial covalent character of ionic bonds through a set of rules called Fajan's rules. And let's learn about these now. Students, Before you learn about Fajans rules, you must first understand what polarization of an anion by a cation means. When a cation is brought near an anion, the electron cloud of the anion is attracted or pulled by the cation towards itself. This leads to deformation or distortion in the shape of the electron cloud of the anion. In other words, the electron charge density of the anion would shift towards the cation. This phenomenon is called polarization of the anion. Now, it is the cation that polarizes the anion. So, the power of the cation to polarize the anion is called its polarizing power. The tendency of the anion to get polarized is called its polarizability. Now, students, imagine a 100% ionic compound. Okay, in a 100% ionic compound, imagine a cation sticking to the anion. Okay, imagine that there is no space between the cation and anion. Just think that the cation is just sticking to the anion. In such a 100% ionic compound, the electron cloud of the anion would lie completely within the anion itself, even if the cation lied very closely to the anion. Clear? Now students, just remember you should have drawn the Lewis structures of a number of covalent compounds. In those structures, you might have noticed that the bonding electrons usually lie between the two atoms that are involved in bonding. So in covalent compounds, the electron charge density is found to be high in between the two bonding atoms. Okay, in covalent compounds. Now, likewise, in an ionic compound, due to polarization, the electron cloud of the anion would be pulled towards the cation. Clear? So, in such a situation, some part of the anion's electron cloud in the ionic compound would lie between the two atoms. And this is similar to what happens during covalent bond formation. Right? So, as a result, the ionic character of the ionic bond would decrease. In other words, covalent character of the ionic bond would increase. Clear? So, the ionic character of the ionic bond formed between a cation and anion decreases with increase in the attraction of the electron cloud of anion by the cation. That is, greater the polarization, more is the neutralization of the charge on the cation by the electron cloud of the anion. So this is about the polarization of an anion by a cation. The following factors determine the percentage covalent character of the ionic bond. That is, these factors determine how much an ionic bond is covalent in character. What are they? Polarizing power of the cation, polarizability of the anion, and the extent of polarization or distortion of the electron cloud of the anion towards the cation in an ionic compound. Shall we learn Fajans rules? There are three rules. The first rule states that the smaller the size of the cation and the larger the size of the anion, the greater the covalent character of an ionic bond. Now look at the decreasing order of covalent character of ionic bonds in lithium halides. The covalent character of the ionic bond in lithium iodide is greater than the covalent character of the ionic bond in lithium bromide. This in turn is greater than the covalent character of the ionic bonds in lithium chloride and lithium fluoride. So, in which among these compounds the covalent character of ionic bond is the least? In lithium fluoride. Okay, remember I told you that the covalent character of the ionic bond increases with increase in the polarization of the anion by the cation. And smaller the cation, greater is its polarizing power, and larger the size of the anion, greater would be its polarizability. So among these anions, iodide, bromide, chloride and fluoride, which anion is the larger in size? Iodide ion is larger in size. So polarization of the anion by the cation is greater in the case of lithium iodide. Therefore, the ionic bond in lithium iodide has greater covalent character and the ionic bond in lithium fluoride has greater ionic character. Now look at this question. The covalent character of ionic bond is more in which of the following compounds? Lithium chloride or potassium chloride? Obviously, it will be lithium chloride. This is because the size of the cation, that is Li plus in lithium chloride, is smaller when compared to the size of the cation K plus in potassium chloride. Since polarization of the anion by the cation would be greater when the size of the cation is smaller than the size of the anion, the ionic bond of lithium chloride has greater covalent character than that of potassium chloride. So, lithium chloride is the answer for this question. Now, the second rule states that the greater the charge on the cation, the greater the covalent character of an ionic bond. So, now look at the increasing order of covalent character of ionic bonds in these chlorides. The covalent character of the ionic bond in aluminium chloride is the greatest as aluminium ion has the greatest charge. See, aluminium has 3 plus, whereas the other cations of the other chlorides, say Mg2 plus and Na plus, they have lesser charge when compared to aluminium ion of aluminium chloride. So, the covalent character of ionic bond in AlCl3 is greater when compared to the covalent character of ionic bonds in magnesium chloride or sodium chloride. Now, the third Fajans rule states that for cations with same size and charge, the one with electronic configuration N-1 Dn Ns0 typical of transition metals is more polarizing than the one with the noble gas configuration Ns2 Np6 typical of alkali and alkaline earth metal cations. So, copper chloride is more covalent than sodium chloride. To sum it up, according to Fajans rules, the covalent character of the ionic bond increases with small size of the cation, large size of the anion, and greater charge on both the cation and anion. So, with this, I wind up my video on resonance structures and polarity of bonds. Thank you for watching my video and bye-bye for now.